In enrichment example 4.2, we're going to take another look at the testing reliability, in particular in the context of fatigue cracks. Remember, people like to use the paperclip as an example of fatigue, although that's not actually at all an example of fatigue. It's just large strain cycles, and that's not quite the same thing. Fatigue is associated with thousands and thousands of cycles of elastic level stress cycles. And we're going to declare here that F is our event, that a member has a critical fatigue crack. And our prior experience suggests that the likelihood that this happens is quite small, 10 to the minus fourth. Right, so that's 100th of a percent. And we have a test to detect these fatigue cracks, and we'll call that event R, the event that we reject a member. Of course, we're going to reject it because we think that we have found a crack. Further, that prior history tells us that we think the probability of an error, that is, that we would reject given that we don't have a crack, or in words here, is also quite small. Not quite as small, but we only have a 1% chance that we're going to make that kind of an error. Reject, but we don't actually have a crack. We think we have a problem, but we don't. Or the other, that we don't reject, but we do have will also be pretty small, only 1%. That would seem like a test that would be pretty good, right? So we're going to ask the question then, if the test says reject, should the member be rejected? Should we test? Or should we trust the test results? Right? And in terms of our probability notation, what we're really after then is we want the probability that we do have a crack given that the test says reject. What kind of magnitude of numbers are we talking about there? In the work that we did before with probability trees will be useful here as well. Right? And we'll start off with the odds that we have a crack, right, which is again quite small, 10 to the minus fourth. And the complement of that we don't have a crack, is 1 minus 10 to the minus fourth, right, or 0.9999. And then last time we had a lot more branches on the tree to consider. Here we don't. Now we just have 2 in each case, right? We have reject or we don't reject. And so our information we have up here tells us what we want, right? So probability of not rejecting given that we have a crack. So this one right here is 10 to the minus 2, or 0.01, and then that makes the other one 1 minus this, so 0.99. Then down below we've got probability of R given FC is 10 to the minus 2. Probability of R given FC is 10 to the minus 2, or 0.01. Of course, that makes the other one 0.99. Now we can go straight and look at the joints. Remember, they're just the product of the branches on the tree, so the probability of F and R is going to be equal to 10 to the minus 4th times 0.99, so a lot of zeros there, 0.000099. Probability of F and complement of R, so probability of having a crack but we don't reject, is 10 to the minus 4th times 10 to the minus 2, so 10 to the minus 6th. Probability of no crack yet we reject is 0.9999 times 0.01, so 0.009999. Seems like a small number, right? And then the probability that we have no crack and the test says that there's no crack, 0.9999 times 0.99, or 0.989901-ish. And what we're again after was probability of having a crack given that our test said that we had a crack. So we go back to Bayes' theorem again, and that's probability of F and R normalized by the probability of R. Alright, so the joint F and R we've already found up here. That's our 0.000099 divided by probability of R, the marginal associated with R. So that's the sum of these two right here. So that's 0.000099 plus 0.009999, and that's going to end up equaling 10 to the minus 2, which, wait a minute, the probability that we have a crack, given that the test says that we have a crack, is really small. It's only a 1% chance. That's not so good here. And what's really going on is that the probability of our event is so low, and the testing is not adequate. And that's because the chance of error is larger than the chance of the rare event. It was a good thing that, gee, our chance of having a crack was only 10 to the minus 4th, but our chance of error was 2 orders of magnitude larger than that. And that really is driving these funny numbers that we're ending up with here, and ultimately saying that we don't have a very good kind of situation. Right? And big picture, then, for a good test, we have to flip this around. We need our error probability to be larger, to be less than our prior reliability. And so these decision trees are really probability trees, and the joint and conditional and marginal distribution relationships really help us to ferret through all of that kind of information. Now we're going to see these concepts come back to us later on when we get into hypothesis testing.